next speaker is Sergey Suetin. Are you here?
Yes, I'm here.
Yes, we can see the screen. And do you have a camera?
Yes, I have a camera, but I have a problem with my computer, and unfortunately, I can't share my picture with you. Sorry, it is some technical problem.
Well, okay.
Good with my slides. Okay.
We can see it, yes.
Everything is good.
Sure. And now the next speaker is Sergey Suetin on some algebraic properties of Hermite-Pade polynomials. Please start.
It is okay?
Yes.
At first, thank you, the organizers, for this kindly invitation. And let me say some words in Russian about юбилярс. Я знаю Никиту и Леню очень-очень много лет. Не то что с прошлого века, а еще где-то с начала 80-х. И мне очень приятно, что они пригласили меня на эту конференцию, хотя никаких общих научных проектов у нас никогда не было. Ни в грантах не состояли, ни в программах. Все, что у нас было общего, это мы состояли в одной комсомольской организации математического института имени Стеклова. Я какое-то время интересовался проблемами, связанными с теоретической физикой. И как когда-то справедливо сказал Андрей Константинович, я ходил регулярно на семинары в отдел еще Поливанова. Но, увы, в этом направлении я так не продвинулся. Поэтому еще раз спасибо за приглашение. And let me start my talk. Since the subject of my scientific research is not very close to the subjects of the conference.
Sorry, sir, I disagree with you. Okay. I think that in my activity, I permanently deal with orthogonal polynomials.
Okay, thank you very much. And I would like to present some of my results. This result is very simple in my opinion, but it maybe considers some interesting result and maybe interesting to, of course, it is very clear and maybe understand by everyone, and I believe it will be interesting to many of participants. So I will discuss some connection between Hermite-Pade polynomials and Fuchsian system of ordinary differential equations. Let's consider the following problem. It is not a big problem, but in some sense it is interesting for each natural m and natural n. Let's try to find two matrices of size m, A and B, which are polynomials in Z, and have the following properties. All elements of these matrices, A elements and B elements, are polynomials of degree non greater than n, but all the diagonal elements are polynomials with the degrees exactly n. Next property is these two matrices are inverse to each other. That is, the product of A and B transpose matrix give us identically matrix. And also we would like that both these matrices to be normalized by this property at 0 point. This values equals to unit matrix. Let me explain the connection of this problem with the subject of Padé polynomials. Let me given the function holomorphic at infinity point, or we may consider a formal power series, which is in some sense in generic situation. And that means in particular that all the indices n of Padé table for this power series are normal. That means if we seek for two polynomials q and p of degree non greater than n, and this relation between q, f, and p polynomials is characteristic relation for Padé approximants. Normality means that on the right side of this relation, it is exactly the right side of this relation starts exactly from this power of z in the power of n plus minus n minus 1. And next, we change the index n to next index n plus 1 to obtain the next equality, which is the following. And it is easy to obtain from these two relations the following relation between q and p polynomials. That is, this combination gives us the value which is bounded when s then tends to infinity point. From this, it follows, since on the left it is a polynomial in z, we obtain from this equality that this polynomial is identical. From normality condition follows that this constant doesn't vanish, and thus we can normalize it to be 1. And thus, if we consider this matrix M which depends on Z, it is easy to check that this the determinant of this matrix equals 1 identically, and thus we easily obtain two matrix M and the inverse of this matrix. Both are given by Padé polynomials. This identity between Padé polynomials numerators and the denominators are very well known and very useful in the theory of Padé polynomials. Many of convergence results were proved based on this formal relation. And in some cases, it is possible to extend the power series from infinity point outside the circle of convergence by this expansion. This expansion, which involves Padé polynomials, is, in some sense, it is a generalization of Taylor expansion, which is valid only inside the circle, and this relation for some classes of function f gives us the possibility to extend this function constructively outside the circle of convergence. So let me go to discussion of the relation between the Padé polynomials and the theory of Fuchsian systems of ordinary differential equations. This activity was initiated by Chudnovsky's brothers, Grigory and David. There is represented only two papers by Grigory Chudnovsky, but there are many papers related to this subject, and all these papers dated last century, and it seems to be that this activity somewhere finished, but fortunately it wasn't so. Some Japanese mathematicians, maybe they were initiated by Chudnovsky's papers, they continue this activity and obtained very recently some new results in this direction. And on this slide, there are represented only a few of papers in this direction. I represent only those papers from this mathematical group where there is the term Padé in the title. There are more other papers without mention Padé term in the title, but in fact, in all these papers, there is a relation between Fuchsian system and Padé approximates. Let me note that Chudnovsky's brothers and also Japan mathematicians, they all use the term Padé polynomials in very wide sense. They also means the Hermite-Pade polynomials and Padé multipoid interpolations and so on. Let me give some introduction in this theory on Fuchsian systems. I'm sorry, I am not an expert in this field. I was interested only in the connection between this theory and Padé polynomials. Let me given this Fuchsian system where AG are matrices, and this system, it is supposed that singularities, two singularities are fixed at 0 point and at the point 1. And there are other singularities in the points T sub G, and there is a standard relation between these matrices. If we try to continue analytically the solution y of z of this equation along along a loop which belongs to the extended complex plane punched at these singular points, then we can go to another solution of this equation, but it is not necessary that it will be the same function. So we obtain some multivariate analytic function in extended complex plane, punched the singular points of the set sigma capital, and the authors of these Japan papers introduce such a definition. I'm not sure that this standard definition, but they used them. They called such transform of y function from y to y with tilde with respect of some matrix R of Z, which is rational in Z, and this transform is said to be a Schlesinger transformation in their notation that the new equation for y tilde function satisfy just the same, just the Fuchsian system of the same form as before. Since this R function is rational, both functions y and y tilde have the same monodromy. And let's consider in what way the matrix A of Z transform under this transformation when we multiply y solution by R function and consider y tilde instead of y. It is easy to check. It is well known that instead of A, we will obtain A tilde, which is given by this representation, by this explicit representation in terms of A and R transformation. And that means if both R and the inverse of it are polynomials in Z, then A tilde turn out to be a rational matrix function, which have only simple poles and at just the same set sigma as the original matrix A. So we consider the case when M equals 2, that is, we consider the case of matrix of size 2 by 2, and the construction of this type Schlesinger transformations was considered by Yamada in this year, and this consideration were based on usual Padé polynomials. And let me also note that when in this Fuchsian system we set M equals 2 and N capital equals 1, then we have that two singular points 0 and 1 are fixed, and there is only one free singular points T equals T sub 2, and then A matrix and the solution Y depends on that and this T, and thus we obtain Penlever-6 equation, and there are some interesting connections between Penlever-6 equation and Padé polynomials. In 1986, John Nuttall considered the problem of convergence of Padé polynomials of this function f of z given by this explicit representation, where the points A1, A2, and A3 are distinct, and the exponents alpha GT are not integer and satisfy this equation, then the logarithmic derivative of this function is given by this representation. And if we consider the problem of convergence of Padé approximants to this function, we obtain that the corresponding to the problem Riemann surface is of genus 1. Thus, there is so-called spurious poles of Padé polynomials for each n, and these spurious zeros of Padé polynomials, which provides spurious pole of Padé approximant, and this pole have no relation to the singularities of the initial function, but this pole has the following property. Let's consider all the Padé approximants are considered at infinity point. And thus, if we said that this function f at z is given by this representation, where we set a1 equals 0, a2 equals 1, and a3 equals t, then and consider some branch of this function at infinity, holomorphic at infinity point, then all the parameters of the problem depends on this value t, and it occurs that spurious zeros of Padé polynomials as the functions of this t satisfy Padé-6 equation. This was discovered at first by Grigory Chudnovsky and then repeated by John Nato. Now let's consider the problem of the extension of this result of Yamada about the connection between Fuchsian systems and Padé polynomials, but for the case when the size of matrices equals m, which is great or equal than 2. So we consider the more general situation, and let's start from the formal power series given at 0 point. Not at infinity point, but at 0 point. Then there is two generalizations of the classical construction of Padé polynomials. One of them is so-called type 1 Hermite-Pade polynomials, and the next is type 2 Hermite-Pade polynomials. And if we consider the corresponding matrices, A of zeta and B of zeta, both are polynomials in zeta, then this then up to these matrices under suitable normalization satisfy the following identity. This is the very well-known Mahler duality property. It was discovered by Mahler in 1928, and these Japan mathematicians, Mano and Suda, made some this Mahler duality to obtain some new matrices, not in zeta but in z, where zeta equals 1 over z, and these new matrices have some special and useful properties, and they start from Mahler duality and then generalize it in some direction. But after some reflection, I decided that it would be more properly to obtain this matrices A of z and B of z directly, not starting from Mahler duality and doing some generalization of it, and then change the variable from zeta to 1 over z. So I decided to to make some new construction of Hermite-Pade polynomials, which is non-classical, non-standard. And let's consider now the tuple of power series. It may be formal, not holomorphic at infinity. We suppose that this tuple is in general position. In particular, they do not vanish at infinity point. And let's discuss this new construction, which is not classical, non-standard. So we would like to obtain two matrices in Z, which are inverse to each, which are in polynomial in Z and inverse to each other. One matrix is based on type 1 Hermite-Pade polynomials, and the second is based on type 2 Hermite-Pade polynomials. And let's start let me explain the idea of this construction based on Padé polynomials. So we consider the case when m equals 1, and we, instead of m function, m plus 1 function, we consider a pair function, and let's consider two multi-indices. The first one n sub 0 and the next n sub 1, which are presented here on this slide. For the first case, we are seeking for two polynomials with the following property, and the new element is that I involve z in this construction. And next, it is easy to see that these polynomials always exist. And when we consider the situation generic case, then this Q sub 0 and super 0 polynomials doesn't vanish at 0 point. So we can normalize it to be 1 at 0 point. And next step is we consider the second multi-index, and this second new construction of polynomials Q1, and also I also involve that in this construction, but to the first part, to the function f sub 0. And we also can normalize this polynomial Q1 to be 1 at 0. And it's easy to see that for these pairs of polynomials, there is such an identity. And from the condition of general situation, we can normalize this identity by the following condition, and to obtain that these two matrices are polynomials in Z, and they are inverse to each other. And the advantage of this construction before the traditional is that we can extend it to Hermite-Pade polynomials type 1 as well as type 2. So we can consider this the tuple of m plus 1 power series with some condition of general position, and consider at first multi-index n sub k with the following properties that all its elements but k plus 1 equals n minus 1, and this element equals n. And let's consider such a construction which gives us type 1 Hermite-Pade polynomials. Here, this z variable is involved to all members of this sum, but not to the diagonal part. And so we obtain that the degree of this, sorry, it is misprint, the degree of this diagonal element exactly k, and doesn't equal 0. And as usual, we can normalize this polynomial to be unit, to be 1 at 0 point. And just the same way, we can consider the similar construction for type 2 polynomials. It is also it is not also non-standard, and I involve that variable in this construction as its part. So this construction also similar and gives us just the same, just similar conditions, that for diagonal elements we have the degree of its equals m times n, and diagonal polynomial doesn't vanish at 0 point, and thus we can introduce the appropriate normalization, and thus we have the following proposition. Let's consider this new construction of type 1 and type 2 Hermite-Pade polynomials, and let's produce two matrices, M sub 1 and M sub 2. The first is based of type 1 polynomials. The second is based on type 2 polynomials. And this, just from definition, it easily follows that these two matrices have the following property. They are inverse to each other, and they both have the following normalization: at 0 point, they equal to the identity matrices. Let me note that my construction is based on the expansion at infinity point, but not at 0 point. From this, it follows that nothing changes if we replace this z to z minus a, where a may be any finite complex number. After that, we obtain new Hermite-Pade polynomials with just the same property, that they produce two matrices, polynomial in Z, and which are inverse to each other. But instead of this normalization condition, we will obtain that both these matrices equals at a fixed a point equals identity matrix. This situation was, I mean, this normalization and some other properties was considered in some papers of Grigory Chudnovsky. They will needed him for some investigation of Fuchsian systems. So this.
I'm sorry, but we have 5 minutes.
Okay, thank you. So the proof of this proposition is very easy. It is based, in fact, on the definitions and of type 1 and type 2 Hermite-Pade polynomials, and it is only 2 slides to prove this property. And okay, I will try to finish at this moment. So Thank you very much for your attention.
Thank you. And we have also some time for questions, maybe.
So,
May I ask a general question? Hello, do you hear me?
Yeah, we can hear you, but
now
you
waiting
next,
for your question.
Oh, the question. Right. I just wonder, I mean, in all your constructions, that people discuss, the variable z lives on Riemann sphere. I wonder if there is an analog in Lever and your Padé approximation when the variable z lives on an algebraic curve of non-zero gene.
Maybe I don't know the answer to that question, since I'm not an expert in Penlever equations. I deal only with Padé approximants and their generalizations. And I mentioned about Penlever 6 equation only in connection with Padé polynomials.
But what about Padé approximation on a curve? What makes sense?
Padé approximations on a curve to what? To what function, which is given as what? Usually we consider a power series given, say, at infinity point. And then we try to extend this power series as far as it only possible in some constructive way. But the approximants gives one such a method to extend this power series outside the circle of convergence. And if you are given a function on the Riemann surface, say this function given in a neighborhood of some point, what is an analog of Padé approximants to this function? Rational function in what? In not in z, but in what variables?
May I make some remark?
It is not a question for me.
Can I make a remark?
In my opinion, you are welcome.
Huh?
Of course, yes, Sasha.
It is just for Sasha question. Well, I have not read it myself carefully, but there is a recent paper by Bertola, which is exactly called Padé approximation on Riemann surfaces and Capet tau functions. So probably there is something kind of known. As I said, I have not looked at it.
Yes,
so I cannot say more. But
yes,
just
I know about that papers. Of course, they are uploaded to archive, and it is well known. But these papers, in my opinion, these papers are not about constructive analytic continuation. They are about some other subject which is connected with Riemann surfaces, generalizations of Padé polynomials. It is possible to consider Padé approximants on Riemann surface, but let us fix a problem in which it should be involved.
Basically, it's the same idea that any rational function on a Riemann surface is a rational function of we can fix two functions, and any functions is a rational functions of these two functions, right?
Yes, of course.
So
Right.
then we can set the question about Padé approximation by these rational functions.
Yes, you are right. In general, in one variable, you start from a given power series in Z. And this function may be a multi-valued analytic function, and may be continued along every path in complex plane, which avoids some finite number of points. So the Padé approximants give a single valued extension of this power series in some domain which is called Stadt domain. And when we consider more general rational functions, you should consider the initial function to be given on a Riemann surface, and say this surface, let's suppose this surface is a compact Riemann surface, and this function should have some branch points on this Riemann surface. Since otherwise this function itself is a rational function on this Riemann surface.
No, I am just looking at the paper of Bertalat. So in a sense, he starts from one of the standard setting of Padé approximation, not just to reconstruct, this Cauchy type approximation, Cauchy type integral. So you have a measure and you want to find it, if I am right. And so he just starts with kind of so-called Weyl functions on the surface. So just as a analog of the Cauchy kernel on the surface, and then you want to reconstruct this function. So if you assume that function whose Lorentz series is given by this type, then you immediately go to the Riemann surface. Okay.
Yes, it was a starting point in Padé approximation theory to consider the function given by so-called Stiltiès representation.
Yes,
or
this is analog, yeah. Mm-hmm.
Yes, this is an analog of these representations. Yes.
If it is still, there is a time, I have another question. Can I still ask it? Or it is already out of time?
Yes, you can.
Huh?
Yes, you can. We have time.
So I'm
Have
just
a coffee break now.
but Sergey, maybe I missed it, but do you address the question about asymptotic Lachian asymptotics of those Hermite-Pade polynomials?
No, I devoted this talk only about the algebraic properties of the polynomials, which have some relation to Fuchsian systems. Nothing about convergence problems. I would like to mention that the main subject of my talk, the main result, is to introduce some new construction for type 1 and type 2 Hermite-Pade polynomials. That construction is not classical, not traditional, but they means the following. Maybe it has some perspective in the following sense. These two matrices, M1 and M2, which one is based on type 1 polynomials and the second is based on type 2, they have the following property: the product of these two matrices equals identically matrices, and thus if it is true for each n. Thus, when we tens n the degree of these polynomials to infinity, this identity stay valid. And thus, if we have the asymptotics for type 1 polynomials, from this identity, it is possible to obtain the asymptotics for type 2 and vice versa. It may be some perspectives in this relation for the asymptotic theory.
Okay, thank you.
Well, thank you again. And now we have a short break, maybe 10 minutes.